Okay, good morning everyone. I hope you can hear me properly. Let's have a quick look, make this volume a little bit better. Okay, so hopefully YouTube will be a slightly better interaction experience than we had with Panopto. I'll try and upload to Panopto the result anyway, but we'll be using YouTube just to see if this works in a nicer way. Anyway, so yes, please use the live chat for questions and stuff like that. I found that really works. Normally when in the lecture I look at your faces and I can see whether you get it and stuff like that. In this case I have very little interaction, so the chat really helps with having some degree of connection with people. Then, exploiting the language. So one of the challenges with programming is how do you write your program in the right way, or how can you use the strengths of the language to make your programming better. And that is what this lecture is kind of about. Okay. So the main part is basically first we look a little bit at Kotlin Java interop, and then I look at various language constructs and how you can organize your code in a more complex project. And you have seen a little bit in the assignment code where I used a little bit of this. So how do Kotlin and Java interoperate? So as you know, hopefully, Kotlin is designed as a language that works primarily on the JVM. It also works on JavaScript and for native. One of the main usage areas for that is that you can use the same code also for iOS applications. But we're looking at Java interoperability here. So Kotlin, basically, it can just call most Java functions by default. If you want to make that slightly nicer from the Java side, what you can do is add nullability annotations. But in most cases, you can just use Java code as is from Kotlin. The other way around does require a little bit more, but things. One of the key aspects in using Java is this whole functional stuff. So Java's functional stuff doesn't work the same as it does in Kotlin. So basically Java originally was not designed to support lambdas. They were not any part of the thought in Java. So no inline functions basically, or create the function in place. Instead you'd have these anonymous inner classes, which are a lot of what we call boilerplate, and they look ugly but they work. And so lambdas didn't exist, so what they needed to do was to add them in a compatible way. At the same time there were all these functional interfaces like runnable, comparable, and many listeners, and the idea is you don't want to have people have to redesign their libraries so just that people can take advantage of this lambda functionality for that library. So what they did was basically said, okay, actually, if we have an interface that has one method that's not defined, so single abstract method, that's what SAM stands for. So that can be either an interface that has one method that is not defaulted, or it's an abstract class that has one method that is abstract. And you know hopefully that a defaulted method in an interface, how that works. So yes, there is an implementation there. So only methods without implementation. There's one, okay, then I know what the body of the lambda needs to be placed at for creating that particular class. So it's an interesting way of using lambdas to create objects or classes that have one particular method implemented and then immediately getting an instance of that. Or the anonymous inner class kind of approach, but then much more concise. And basically Java then has no function types. You cannot create a type for functions in general, but it does have functional interfaces that can take that place to some degree. And there's a lot of built-in ones as well if you want to use those. And yeah, it's not as neat and tidy as Kotlin's function types are. So what does this look like? So this is one of few examples of Java in this lecture series, this unit. So this is an example of a functional class. So we have the functional interface. In this case we call it transformer, that needs to do some transform implementation. And then in our main we just create an instance of that transformer and we assign that to this lambda. So p becomes p times 2. I could have named it x or whatever I wanted it to do. That's all a lambda is in Java. So it looks slightly different from the Kotlin one. There's no curly parentheses involved in this particular case. This is a Java lambda. And then we can print line, we can call this transformer with do transform 2, do transform 4. So this prints out 4 and 8. Kind of boring what it does, but you can see how this works. So one of the things that we find here is like the interface just is a regular interface. When you're using it, you just use it as an interface. You don't get to have this nice functional syntax like we have in Kotlin. That's a disadvantage of how this works. And another point, and there is this annotation called @functionalInterface that basically gets the compiler to check this for you. That's what the annotation is for. So how does this work in Kotlin? So Kotlin supports this if you are calling into a Java interface. So if the interface you're implementing is defined by Java and not by Kotlin, and it can somehow detect that, yes. Basically for Kotlin it adds some extra information because Kotlin's type system is a little bit richer. It needs to add this and it can say, okay, I know this is Kotlin, therefore I'm not going to implement that by hand. So do that. So they actually changed their mind and it will be available for Kotlin, but it's now only released in 1.4 milestone 1. So this is a testing release, a beta release for development. So that is not something yet ready for production, but it will happen. But I think they released it just a week ago, something like that. So that will happen, but for now it only works for interfaces declared in Java. Of course, what you can do is declare the interface in Java and have everything else be Kotlin. And then you can have this work. There are some snags with SAM conversions because if you have a SAM class, so by default, Kotlin interfaces have certain interface, Kotlin lambda, sorry, where they don't implement this particular interface. So there is some snags with that, and so you need to be careful with those things. So what we find also is that, yeah, the types are named with SAM interface. So there's some advantage of having them, and that's partially why we want them for Kotlin, even if we do not have the Java compatibility need. So Then there's a lot of annotations you can use for making it easier to use your Kotlin code from Java. Obviously in Android, if you're making an app, that's not so important because you can just determine everything. But if you're writing a library, that becomes much more important if you want to reuse this code either from Java or from Kotlin. Your user could be written entirely in Java and shouldn't need to care that you wrote your things in Kotlin. And you can do that with Kotlin with a tiny little bit of care. So Kotlin code normally can be used as is. So, but there are some things to make it work better. So there's some basically annotations that you can use to tell Android Studio or IntelliJ or in fact the Kotlin compiler for that. So the idea is that we have functions that in Kotlin exist as class level functions. So yes, so hopefully the stream will stay on. I've got it on low latency. That might be the issue. So when you create a function that is not inside a class, it will be a package level or a file level function in Kotlin. And the way that is actually implemented if you're compiling to the JVM is that it will create a class and it creates a static method inside that class. The name of that class is whatever the file name without the .kt, and then we add kt with the capital T, K, and then a T. That's where you can find these functions. There's a number of different things. You can also actually merge the functions from multiple different files into the same class if you want to. I don't cover that here. But if you want that class to be having a different name, for example, we want to do the Kotlin version of math, so Java lang math, or Java util math, sorry. That is just a class that has a lot of helper functions to do all these math operations. We wouldn't want to do it that way in Kotlin, but if we wanted to, we could do that and then have a file, add file column JVM name to set the name of generated class. That needs to be at the top of the file to work correctly. If you don't do that, it will give you a warning and will tell you to put that at the top of the file. So another point there is that if you have extension functions from Java, that extension function is just one that takes the receiver as the first argument, as it in the end actually does anyway. So yes, looking at the Java compatibility does help you to understand about how it actually works. Then we have JVM field. So sometimes, in Kotlin, whenever you have a val or a var that is not private or that has actual explicit getters and setters, then it will create a private field for it and the getter and setter functions. And in most cases that is the correct behavior. That's also in Java the suggested behavior, how you write good code, but it is also something that we want to make work correctly. And from that perspective, sometimes we don't want that. We want to actually have a public field, especially if you have Java types that you just want to translate into Kotlin without changing the interface, because we do not want to break the interface. I'll come back to that later. So what you can do is just use the @JVM field annotation and it becomes a field. Another point where this really becomes important is if you have constants. If you have constants that you put on a class, even if, so like static final fields basically in Java, those constants still have a getter and setter in Kotlin. Unless you actually, so if it's a primitive, you can use the const keyword and then it doesn't. But if you use a non-primitive value, then it's not a constant as Java means it, and then because we still have the getter and setter generated. Sometimes we don't want that and you don't need that, so you make it at JVM field. Same thing with, so if you annotate something as JVM static and it's a method, then that becomes a static method on the class rather than on the companion object. So what the class static method does, it will actually forward this function call to the companion object. So the companion version will still exist. But all these annotations do not change the primary interface. They just change how it is visible to Java. And finally, we have default interfaces. Or default interface methods. So Kotlin supports default interface methods on older versions of Java. It can work that on 1.6 Java, and default interfaces only were implemented, I think, for 1.8. Could be 1.7. So Java doesn't support default methods in interfaces at lower levels, so Kotlin had this working for 1.6. So basically what is the case here is that Kotlin therefore has a different way of having that implemented. However, if you're using Java, you want these default methods to be available there as well. So what you do is you use the JVM default annotation, and then in your compiler arguments you would tell it how it needs to do these defaults, and you can either configure it to use a version that basically has both approaches there, one that only uses JVM default interfaces and one that only uses the Kotlin approach, of course not with the JVM default annotation. So this makes it possible to have your code your default interface implementation work correctly when you're calling them from when you're using your interfaces in Java, when you're implementing them in Java. However, one of the things I would say that is something you want to be a little bit careful with is mixed interfaces. If you have an interface in Java, an interface in Kotlin, and then you have a class in Java that implements that, and you have a class in Kotlin that inherits that, at some point that can become a big mess, and that's where some things like, is a property do you use getters and setters, or do you use properties, etc. That becomes then problematic. So you don't really want mixed hierarchies too much. Okay, there's some other ones. So JVM name cannot only be used for your file name or the class that is generated for your file, but you can also change the name of a function entirely. And you'll see some example later where we might want to use this. And there's kind of two cases where it's really important. So one of it is if you have a particular name that in Kotlin makes sense but in Java doesn't. The other one is the Kotlin language actually uses generic types at a deeper level than Java does. And so you can have two functions that to Kotlin it can distinguish whether it's so if one function that takes a list of strings and the other one takes a list of integers, to Kotlin they are different functions. To the JVM they are the same functions. So what you can do is use the @JVM name annotation to give them a different name on the JVM. And this is not only for Java compatibility, but this is also to actually be able to implement that. Because otherwise your compiler will say, yes, these ones have the same name on the JVM, you can't do this. So one of the ways you can do that anyway would be to give them different names in Kotlin, or you just use the @JVM name annotation to rename one of them into something that does work. And one of the things, so we have these default arguments in Kotlin. By default, so the way that works is that there's still one function and then it does some kind of a magic to determine whether it needs to fill in the default values. And that doesn't work easily with Java, obviously, because it doesn't know about this magic approach. So instead, what you can do is put the @jvm overloads annotation, and then it will generate a the function with the various options of the default things set or not. One thing, it does not support the named parameter thing, so that's where you kind of break down a little bit. And finally, there is the JVM wildcard. So there's more, and if you want a lot of detail, go to look at the documentation I provided in the title slide here. The JVM wildcards, there are some cases that generics are not generated in the way that works on from Java. The @JVM wildcards helps you to fix that, basically, and gives Java a little bit more leeway. So then, what kind of things do we have in Kotlin that are really different from Java? Some language constructs that can be quite interesting. The first one I'd like to talk about is these companion objects. I mentioned it before. And in Java we have static members and static fields, and one thing I know about static is that it's very confusing for students. Hard to see what we're talking about. So companion objects basically are Kotlin's approach to this. So they are less confusing because we don't have to sprinkle static everywhere. There are some disadvantages in some cases, but in general it's less confusing. So in general we have these objects. So hopefully you remember I did talk about it before. So an object is just Kotlin's implementation of the singleton. So there will only be ever one instance of an object, and it's created automatically. The first time you use it, the JVM will load it and then initialize it. So you can treat it as if it was created at the start of the program, even though that's not technically how it works, because the JVM loads your code on demand always. But what does this companion object do? So a companion object is an object that is linked to a class. That's why it's a companion. And you can actually have named companion objects. You saw that with parcelable. So if we have parcelable, we can give it a name. So we link this object to this class. Okay, why is this generic stuff there? Sorry, I will fix the slide later on, but that generic stuff doesn't belong there. I don't know why it's there. Yeah, no, it's in the slide. Anyway, so we make this object available through the companion. So if you create a companion object, it also creates a companion field on your class. Or if you do type.companion, you get the object. From Java you get the field. The interesting thing that distinguishes a regular object from a companion object is the companion object actually has access to the private members of a class, and you can access the members, the elements inside the companion object as if they were on the object itself. Like you would do static methods in Java. You can do type.thing. You can do type.companion.method or type.method. It's exactly the same. So it replaces these static fields and methods in Java, but a companion object is actually an instance of a class. It just happens to have only one instance. And because it is an object that implements a class, you can use inheritance with it. It can implement an interface, like for parseable, the creation interface, so the creator interface. And you can inherit classes as well. So there's some really interesting things you can do with these companion objects. And of course, inheriting code is always helpful for that. Then you have operator overloading. So what we'd want to do is so basically, what is operating overloading about? Operator overloading is basically the idea that we want to define our own operators in some cases. So we have all these plus, minus, times, divide for integers and other primitives, but sometimes we want to define our own ones. And that is what operator overloading can do. So sometimes we also say, so why do we want that? So sometimes we have our own number types, or Java has those already. There's something like big decimal, or big number, so a big integer. Those are numbers that are bigger than a long can contain, or a double can contain. Arbitrary precision numbers. They are still numbers, but we want to be able to handle. There's complex numbers as well. So in Java we have this really, really clunky business with when you use big decimals or big integers, where you actually have named functions rather than the operators, and it just makes things look very messy, very clunky. So we want to have our own operators to kind of make this much clearer. Kotlin does not give you the freedom to define any operator you want. There's other languages that do allow that. An example for the JVM is a language called Scala. That also means that you can go completely overboard and make things become a big mess. Don't do that. So Kotlin only has a fixed set of operators. What you can do, by the way, is have infix functions. So you can have a function that actually allows you to basically have a receiver and a parameter and then not have the dot and parentheses needed. You just type the name. It's quite helpful. There's a function, default language function that does that is, for example, to. So A to B. That actually creates you a mapping entry that with an infix function, so a pair. So there are many ways, by the way, if you use operator overloading, and then one of the reasons that Java doesn't do it, you can shoot yourself in the foot very well with operator overloading. So try to stay sensible with this. So what does this look like? For example, you have the operator function plus, that's addition, function minus for subtraction, times for multiplication, div for division, and dot dot for the is the range to function. So if you have a range, that's how you create that. So if you want to make your own custom range, you implement that, and then can use the dot dot. You have plus a sign, and there is a typo there. It should not be plus minus, it should be plus equals, as you know. Wrong key, etc. And there's many more available. There's logical operators, etc. So have a look at the documentation for that. But there's also a few that are special, and I would put your attention to this. So one of them is the operator invoke. So invoke basically means that you can have an object and you can just use you can treat it like it's a function name and call it. So in Kotlin you could have a way, because these operators, they can also be defined as extension functions. So if you have a SAM interface, in Kotlin you can write the extension function that has the operator fun invoke, that then calls this, so that in Kotlin you could actually, using this extension function, make calling the name of that particular interface's method completely disappear from your code. It makes it much clearer what happens, because it effectively is a functional thing, so we should just be able to call it. And if you make it an inline operator fun, then that code entirely disappears from the runtime. Then we have the operator fun get. You have seen this in Matrix, for example, where you basically use this to get array indices. So you can have multiple indices, and that will translate into multiple parts between the square brackets. So in this case, the operator fun get index gets our value. Operator fun set sets a value. And yes, you can have multiple implementations of these that take different parameters, either different value types or different index types or multiple indices. And I think Matrix does this, for example. It has one get that takes a coordinate and one get that takes an x and a y value as separate integers. So those are these special operators. So with this you can basically make your types a lot easier and to read from a user's perspective. That's what we want. We want making use of a class become really clear and easy. Then, transparent factories. So what are factories and why do we want to make them transparent? So factories, I'll come back to that a little bit because that's our code pattern of the week. So a factory is basically a thing that creates an instance of a class. And there are some cases in Kotlin, I don't know if you've noticed, but if you have a constructor that basically the first thing you have to do is call the parent constructor. Sometimes what you want to do is do some calculations before you do that, so that your parameters can be translated properly into the parameters for that parent constructor. Sometimes it's possible to actually use use secondary constructors to do that transformation for you in some forwarding way. Make them private, obviously, or make some of them private if they're only for internal use. But in some cases that's just not really easy to do. So if you want to get these field values, you might want to basically have a way of creating that, an instance of that thing that does a calculation and then actually creates the thing, but does so transparently so that your users don't need to care. And that is what these transparent factories do. And what we can use there is to, so in another case is what we call reified types. I'll come back to that again later. What are reified types? But basically sometimes you want to be able to do that. I will show you some examples later. And in general, the third reason why you might want to do this is sometimes you can actually reuse instances. Either because you have a cache of the last values, and if it's an immutable object, there's no reason to create yet another one of the same immutable object. Sometimes we have a constructor that takes an interface, but the object itself implements that interface and can be a wrapper for those things. So like we have an object that has a handle, and the handle, the object itself is a handle to itself, but you can also have a handle that doesn't point to it. So what you can do in such a factory would be able to say, okay, is this handle actually already an instance of this class? Then return myself. Otherwise, I'll create an object that looks up the thing, etc. So that is, or creates a new handle, whatever needs to happen. So basically you can have more flexibility. Or in Kotlin example, we have the list of factory. That's not a transparent factory, but it is a factory that creates as a list of elements. But if we give it 0 elements, it creates a special type that's only for empty lists. If we give it 1 element, it creates what we call a singleton list. Again, a list that only has 1 element. It doesn't store things in an array, it just stores 1 element. Only if you have 2 or more elements, it will use a different type. And it could choose based upon whatever it wants, what instance it's going to use. But that's not a transparent factory. So yes, by the way, if you have questions, please put it in the chat. I can read the chat. So you can even answer it from each other. Anyway, so how can you do this? So there's kind of 2 ways that you can do this. The first way is to actually have a function that's just a free function that makes this work. So we have our class that we give an internal constructor because we don't want this to be our public interface. In a way, we would want to have a file visibility, but so where we can have a private class, and then the function A would be able to see the private class because that's private to the file. If we make it it's a private constructor, that private would be private to the class rather than to the file. So we need it to be internal in this case. Yes, some more visibilities would be nice. Then we have this function A that functions as a constructor. So we give it a capital A name. We give it the same name. That's valid in Kotlin. But we cannot really do this in Java in a way, but we can do this in Kotlin. And it looks exactly the same. So make sure it behaves as if it should here. So why we would want to use a private constructor? Basically, you use a private constructor in a class when you have another constructor that's not private, and you might want to do some checking before you use the private constructor, or you have a factory function that is inside a companion, and then it can access the private constructor. If you want to police how your objects are created, you make it private. Obviously, you need to then provide a way for those objects to still be constructed. Normally that involves either secondary constructors that are not private or primary, or the companion object. So in this case, what we do is we have a number as a string, and then we check is this start with 0x, then we make an integer as if it is a hexadecimal. Otherwise, we give it if it starts with a 0 only, then it must be an octal number. These are Unix conventions, doesn't really matter. And otherwise, we just say it's a decimal number, and then we create an object with that number, and it takes a null value. And here is also where you can see we have the constructor parameter x and we have the property x. The parameter takes a nullable int. The property is actually a non-nullable int, and this is one of the cases where you say I actually want to declare the property and the constructor parameter. And constructor parameters are only visible inside the main line of the code where you have this initialization of your object. So don't do really surprising things and it works well. So you don't need to give it a different name. It knows that this x that you assign to x is the constructor argument rather than the property. And if you look in IntelliJ or Android Studio, you will see that they will actually get a different color there. So you can visually distinguish that this is a parameter and the other one is an attribute. So the formatter I use for these slides doesn't distinguish that. It doesn't look at the code that carefully. So, and yes, you could also instead use an extension function upon a companion object. because in Kotlin all objects have a companion. So, or kind of sort of have a companion. But it's kind of pointless to do that because you can define it on the companion itself, or you can have a free function. From Java, an extension upon a companion is not really useful at all, because you don't want it to actually need companion state. So how you use a companion, basically the same. So in this case, the constructor could have been private. So there's an advantage of doing this. And here you see also that we use the JVM static and the JVM name parameters. So JVM static makes this available as a method on the A class from Java. And then we have the JVM name where we call it, we call this a function not invoke in Java, but we call it off. So in Kotlin it thinks that this function is called invoke and it's an operator. And we want it to be an operator invoke because then we can just create it as if it is just a constructor. It looks like it's a constructor from the using code. Not in the compiled code, but in our source code. But in JVM, one of the ways that you can create an object or convention is to call it off. So we get a.off 8. So we get whatever object belongs with that. And that's one of the ways you can have a factory. I mean, there's different conventions for factory naming. This is one of them. And so it can make natural Java access. It's slightly less straightforward, but it does allow you also to have private constructors to kind of close it off really except for inside the class. So it might be better to do this rather than having the free function. Although free functions are also quite popular and work well as well. Then generics. So what are generics about? So generics are about the ability to kind of create a family of types. So we call it, officially it's called a dependent type. So you have a type that's dependent on parameters. So basically you want to give parameters to a type. So this is not a type that is single but has parameters. So a common use case for this is like containers and lists, but there are many other cases. If you have arrays with a particular length, you might want to have the length part of the type. You cannot do that in Java or in Kotlin, but there are languages where you can do that. What we can do is types as parameters, and what that does, it is creates a family of types that are mostly the same, but they are not the same. So we have a list of integers and a list of strings. They are different things. Integers are not strings and strings are not integers. So you can't assign a list of strings to a field or a variable that expects a list of integers or the other way around. And when we look at the setting values, it becomes even more challenging. So basically that's what generics are about. So a very basic example of kind of how this works is this example of code where I actually use it with parent-based child classes. So how you could do this instead. And you see the clunkiness that we get. So we have this base class that has basically an array of elements, has elements. So this is a very, very, very basic implementation of lists. You don't really want to use this, but it's slideware. Code that fits on your slide. It has to have some restrictions because of that. So we have this storage, that's an array of 20 elements. And then we can get elements out of that using the get operator with a single index. And then we read the element out of that, and we have a doSet function. This one is protected. This function is only valid to be called by child implementations. So base list could have been abstract even. Maybe it should have been abstract. Not because it has no implementation for anything, but because it is not valid in and of itself. It's not usable because you can't change values. So maybe I should have made the example to be abstract. Then we have the string list that actually implements this by saying, okay, when we get the thing, I am going to guarantee it's a string. So I do the casting. If you use generics, even in Java, the caller will do the casting effectively. If the caller says, okay, this is a variable that needs to contain a string, and this is a list that I know is strings, but it's actually the raw type is object, it will do the casting. So in this case, the casting happens in this type rather than in the user, but the end effect is obviously the same. So we have, in this case, we need to do the cast to the type because we have an array of nulls. We know it's not a null or an object. We know that it's a string or a nullable string because the only way to set values is through the set operator. The set operator takes strings, in this case not nullable ones, so okay, yeah, maybe it should have taken a nullable string. And then that set operator calls the doSet, and this class should be final, should not be inheritable. So this is the way it works. But it always becomes a little bit clunky. And if you have a chain of derived types, it also doesn't really work that way, and compatibilities start to become really tricky, and you need to have extra interfaces for only reading rather than for reading and writing, etc. So, and it is a lot of writing work, and generics basically takes this all away, and it removes a lot of needs for casting, because before we had generics, when you use the list, you actually had to cast the value you get out to the right type that you knew it was, but the language couldn't tell you. So our generics, when you have these generics, when you have these type parameters, so you put them between the angular brackets, there's two ways of implementing that. There's one way of calling it reified. Basically, that means that you actually somehow push this type parameter into the code. That you actually say, okay, I'm not creating a list of any and then doing casting. I'm creating an array of that particular type. I am using this type as a base point for my code. So we record basically what the type is, and we actually implement variants. And obviously those implementations have all the things to make it work correctly. Because one of the things you can do with these families is that say, okay, there's a lot of code that is really the same, or I know I'm getting something that at least if I use a getter, I will get an object. It can be a string, an integer, I don't care. I can work with that. Or whatever is the type, that's also what I'm going to return. So there's a lot of things you can do with generics and generic functions that can kind of keep track of, I know what the type actually is, and I'm going to use that later on. And for that you do not need reification. Reification really means that you can, in the implementation, know what the type is. You can inspect what the type is, that is the type, that's the parameter. The other option is erasing that information. That's what Java does. So when we look at the JVM level, for most intents and purposes, the generic parameters are gone. You can actually do it if you create an object that has no generic or class that has no generic parameter, but implements an interface that has a generic parameter, or a parent class that has a generic parameter. You can then figure out what the value of that parameter was, because this particular class has no variance, and it can then look up through reflection what the type was. And so you can kind of do it in a manual way. Not ideal. because you have to have a class for every version, whereas reified generics like C# does this all automatically for you. And it doesn't even happen by the compiler, it happens by the runtime, because the runtime can do this. And one of the big advantages, it can work properly for primitives as well as for objects. In Kotlin it kind of works also for primitives, but not as efficiently as if you use the primitives variants of this. So sometimes you want to know the type, so one of the ways that you can do that, or a poor man's version of this if you don't want classes, is to just in your type record the type parameter with a class field. So you record the type that you want to use, and then you have your reified type. So how does that work? Because it's something you surprisingly often want to do. So for example, we can do that in a function, in particular this filter as instance function. So this is a built-in function into Kotlin, and I have just copy pasted the implementation. I've removed all the documentation to fit it on the slides. So we can get all strings out of this list. So this will print string only, and all the integers, that will print 2 and 5. It won't print 5.0, it won't print 3L, it won't print string. So this filter as instance is implemented as 2 parts, just because they find this is an easier way basically to share the implementation. So filter as instance is implemented as a filter as instance 2 with an array list parameter. The array list is just where is this going to be stored, and that is returned as a return value. So the filter as instance 2, because normally you don't care about passing a list where you want to add the elements to. Sometimes you do, because as you can see, that list doesn't have to be empty initially. You can add it to things. So if you have multiple sources where you want to get your stuff from, this is a way in which you can make that work correctly. So what this does, it will create as a list of the elements of that particular type. And filter as instance 2 basically checks for every element in the receiver, that's a collection, that is the iterable that it takes. It checks if it is an instance of R, and in that case adds it to the resulting list, and then returns the destination. So that's a type safe way of getting all the elements in that list that have that particular type. But the way it works, it is that it's done all through reification. That type is basically passed along. In this case it's fully inline, but you can also use the, in this case, C::: class thing to get the class object, and then you can use the class.cast or class.isInstance methods. So how does this work, for example, for a class? So in this case, for a class we want to store the type. We have this type, and we would use so we have this type, and then we want to hide the use inline factories to make this hidden. In this case we don't care about making this constructor private, because maybe someone wants to explicitly pass a class rather than using the reification. Sometimes you do only have a class object, and that's valid as well. So this particular is just a collection that checks the types of an element before you add it. So because generics are erased at runtime, there's no actual checking when you add stuff. It only checks when the values that are received from the element are used or stored. So the user may check the type, but it's normally much better to check the type when you add elements rather than when you get them out. Just the cause where you put the wrong element in is much closer to adding than you do a lot of code, and then at some point you're going to read something out of the collection. So in this particular case, what we do is we check, is this type, so is this element an instance of the type? And if that's not the case, we throw the illegal argument exception. And normally we just add the element and we just from the data. So it's just a delegate pattern. So that is how we do that, and this is then how you would actually hide it away with an inline factory. So we just have a checking collection T that takes a reified generic parameter. It has to be inheriting any, because the type of class T does not allow you to have nullable types. It also does not allow you to have primitive types, so it has to be any. That can be a little bit annoying sometimes, but that's the way it is. So we have a checking collection that checks those types. So here you see how that works. And then of course that collection is the same as on the previous slide. So we just have this very quickly. We have a reified factory.checking collection and with the parameter. Okay, so or it should not have reified factory dot actually. I think this is just when I wrote this, there was a completion thing. So it'd just be checking collection. I will fix this in the slides later on. Then a very cool feature that we have is delegate properties. So what are delegate properties about? Delegate properties are about when you have properties that you want to have getter-setter behaviors that are actually always the same. So you want to be able to reuse code, but obviously there are separate properties and there are some bits that are not the same, obviously. And what you can do is basically use delegate properties. So delegate properties, what they do is they allow you to have rather than having to write the getter-setters yourself, what you do is you have an object that has a getter and a setter inside it, or only a getter obviously, that then gets called when you get or set that property. And those implementations can then reuse that code in whatever way is appropriate. So we want to be able to basically reuse property getter and setter implementations. So by using classes for that. So what is required to make this work? So you need to have basically the delegate needs to have an operator get value with this particular signature. It needs the parameter this ref. So look also at the documentation of course, that passes it the implementation of that operator will get the reference to the object on which the property is declared, as well as a property object. The property object allows you to look at what is the name of the property, what's the return type. So that's basically introspection you can do there. And it needs to return whatever is the type of the thing that's returned. So yes, that could be a concrete value rather than a generic parameter. So maybe that T actually normally belongs to the class rather than the thing. So, and if you want to set values, that kind of works basically the same with set value. And that's all you need to get a delegate property. You need to have these operators defined. They can be either members of the class or they can be extension methods. So if you have a type that you want to use as a delegate, you can actually write an extension method that allows you to use it as a delegate. And there's some really interesting example with maps. because there's some standard delegates. So there is, for example, the lazy delegate. I showed you this one before for the lazy pattern. So the lazy delegate implements the lazy pattern for you. So you have a property that's lazy. You just create lazy. It takes a lambda as a parameter. How do I initialize this value? It takes a function with the initialization, but that will only be called once on initialization. And the interesting thing with this implementation of lazy, it actually has a number of options, and you can basically, it is by default, it is thread safe. You can ask it to create a version that's not thread safe, and it won't do any checking when initializing it. So there's different ways of making this work correctly with lazy that you would really not want to implement yourself time and time and time again. It's kind of tricky to get that right, and it's always the same. So lazy is a very, very useful delegate to use if you want a variable that is expensive to calculate, and you maybe not even know that you need it. Or sometimes there is the case that when you initialize your class, you cannot validly create it yet because some other properties need to be created first, or there's a circular dependency of some sort. So lazy can often help with that. Then there's observable. So observable allows you to basically have a property where anytime it's changed, this will trigger a function to be called. So observable takes some parameters that basically say, okay, this is what gets invoked or informed when there's a change. Very useful if you have objects that basically inform views that their content has changed. So you make the attribute observable, you make that the implementation of the observer, then send a message to your registered observers, and then from a property change we can observe changes of the entire class. And one thing that Kotlin implements is the ability of using instances of the map interface as a delegate. This is implemented as extension methods on map. So how does this work? So it only maps with a string key. What it does, it basically, when it needs to get the value, it looks at what is the name of this property. It uses the name of the property as a key into the map, and then it gets the value or sets the value for setting. So that's how you can use a map as a way of representing your data. It's not the most efficient way of working, but sometimes if you have a map and you might want to expose those as properties, it is a good way of dealing with that in that particular case. And this is built in. You can also very, very easily write your own ones. There's a very, very interesting element as well, that is delegate providers. So sometimes you want to be able to actually, so a delegate gets to inspect when you get or set a value. But sometimes, and the function that creates the delegate creates a delegate, but that function cannot inspect the property it is created on. So what you can do instead is this other operator that is provide delegate. So when you create this delegate, so by the way, a delegate you do is like property X by this particular function that creates me a delegate, or a constructor that creates me a delegate. So what provide delegate does, it basically allows you to create a delegate. In this case it's a member delegate, so a resource loader might in this case actually say, okay, if you want a delegate, I need to check that this property actually exists, and then it creates a resource delegate that actually gets the property That's the actual delegates that is used. So you basically, in provide delegate, you get to kind of provide a map between an object that is used to create a delegate. So when you create an object with provide delegate, you have an object that then somehow has this provide delegate method that then will create as our actual delegate. And this allows us to kind of be there in the construction phase. And this can be very powerful. One of the things is that in the construction we now know the property. So if we look at the class myUI, what we can see here is that we actually have the bind resource ID.ImageID, but we actually now already know the name. So the check property can check that the image name exists at that particular point in time. So so the alternative would be that we would actually have to pass the name as part of this. So check property can here check this. Or sometimes you want to, if you want to have a class that can know about its members, then it's important that these names are registered. Or you want to have a property, a delegate that knows its name, that is introspectable rather than, okay, on getting and setting, I get this property, I want to always have this name, then you need to use provide delegate. And so this case, so bind resource knows the name of the property it is being used on. That's what provide delegate gives us. It's a quite advanced technique, not something I would expect you to use for your assignment at all, but it's quite interesting and useful. The next session is code organization. How do you organize your code and why do you do that? So code organization has two purposes. One of the purposes of code organization is to make it easier for the developer to know where to find what and to keep things separate. The other one is to basically have different scopes. So one thing that is quite different in Kotlin from Java up to version 9. Version 9 does this a little bit, but then in a somewhat hard to use way, is that modules are really part of the language. So in Java 9, modules are kind of, you can define modules and then you can say, okay, these are the packages in the module that are visible and everything else becomes invisible and only internal. But in Kotlin, that works at a much more refined language. Kotlin has modules really as part of the language, and you can have a internal visibility. So an internal visibility for an object means that it is only visible by code inside the same module. So Kotlin basically realizes that if you want to stay sane when managing a project, you use a build system such as Gradle. There's others, Maven, and they understand the notion of a module or a library. And the visibility of internal means that we only stay inside. And Kotlin allows you through that to basically express this restriction. And why do we want that? Why is this really important to be able to do this? And why do we need this visibility? So this comes to the problem when we are writing libraries, what we end up with is that that you want to be able to change your library in the future. But at the same time, you have other people that are using your library and do not want to change their code when they update your library. So there's two forms of compatibility there. There's the binary interface compatibility, which means that it's compatible even if you do not recompile your code. And there is programming interface compatibility, so that is source code compatibility, That means that you do not need to change your program, but need to recompile it. So for example, if you went from a free factory function to a companion factory function, that would not change your source code compatibility, but it would change your binary compatibility, because the function is actually defined on the companion or on the file class. Those are different classes, and that is recorded in the class file that uses this. This is the function or that's the function. They are different functions. That Kotlin doesn't require your source code to know this class to be able to find it is a great feature of the Kotlin compiler, but that doesn't mean that it is not that is the case for the JVM. So that would break binary compatibility. There are ways you can then forward stuff and deprecate stuff. There are ways you can kind of make this work somewhat, but that is what you do with binary compatibility. But there's a lot of things also that break programming compatibility, source code compatibility. So if you add a function to an interface that's not defaulted, that basically means that everyone that implements the interface now needs to upgrade their code. This is an interesting case because this is only an API incompatibility. It is not a binary incompatibility. If you have a class in Java that does not implement all the methods of the interfaces, it will work fine as long as you do not call that function. As soon as you call that function, then the JVM will say, yeah, but there's no implementation here, crash or throw an exception. But if you do not implement the function and you do not call it, it will be fine. Of course, when you implement the source, you do not want to, you have to meet the expectations. So if you have a default implementation, that works correctly. If it's a JVM defaulted one, because the JVM has to implement that. So if you know that your code is never going to be used with Java below 1.6, by the way, for Android you need 1.6. But if you don't have Android and you know it's not going to be used below 1.8, use JVM default everywhere. Use the JVM interface default method implementation, because that makes it work better in this particular context. If you have a function that's public or you change the signature, so public or protected actually. So protected is public for API purposes. It's just only limited to inheritors. But as long as someone can inherit, so if it is possible for external code to inherit your class or your interface, or an interface doesn't have protected visibility. But if it's possible to inherit your class from outside your module, then that becomes part of your public API, that method. So if you remove this, anything that uses that function will crash, either binary or in the programming level. If you have a function or a class and you make it final, that means that anything that overrode that function or overrode the class or inherited the class would now be invalid. That breaks code. Of course, if you have a closed function or a closed class that's final, basically, that cannot be changed, if you then allow that to be inherited, that normally works correctly. Again, there are possibly exceptional cases where it wouldn't. Or if you have a class that implements an interface and you no longer implement the interface, that breaks compatibility. Or even then, this is a nasty one, if you have a public constant, if you have a static final primitive in Java or in JVM, what the compiler does, it will actually copy the value and put it in the place where you use that value. And so if you change the value of such a constant, this may be an API breaking change. That depends a little bit on what the meaning of a variable is. If the constant says this is the version that I was compiled with, then you can use it actually as a way to say, oh, you were compiled against an old version of the API. I'm giving you old version compatibility. However, if you are using it for something else, then that can become a problem. Of course, if it's not public, if it's invisible out for code outside your module, it doesn't matter because a module is always compiled together. So that's this compatibility thing, and that's why we want to have modules. Because we want to be able to limit the visibility, because everything that's not public does not break compatibility. And anything that you make public, you can expect users to use it, even if you say this is actually only for internal use. We find it often that many Java libraries have the internal package, and they actually have public members in such an internal package. Why? Because there are particular things you need to have access to that, but it's kind of used as a warning flag. If you go into an internal package, you may have to update your code if you go to a new version, because it's internal. It's there because sometimes there are some things we know people need to do, but we don't know what is a good public interface to allow this to happen. So we give you a little bit of a hand inside. Of course, another thing you can do is using Java reflection, and you can get at stuff very much. That's just something that is unsafe. The way you do that is using a class called unsafe. Hint, hint. So just don't do that. Next, nested functions. So you can actually use nested functions in Kotlin. So in Java you cannot nest functions. JVM has some support for that, but it's broken. Even Kotlin doesn't use that support in the implementation of nested functions. But nested functions are actually quite useful. So what you do with a nested function is you can put the function inside the body of another function. That's all. It's not really hard, but why do you want to do this? The idea of having a nested function would be that sometimes you have functions that, say, delegate a lot of their functionality to another function, helper function, or if we have a recursive function, we use that. And basically what happens here is that so if you nest this becomes only visible inside that function. So the helper function becomes invisible. It becomes not possible to call this this function without going to the right place, so to speak. And a nested function can also access actually the variables in the outer context. That's quite useful in many cases. And it also allows you to sort your code. So that means that a nested function is even invisible from inside the same class. It's more private than private. So it also makes easy to organize your code. The key part of code is how is it organized? How does it work? That's why we have formatting rules, style rules. That's why we have naming conventions. That it's just easy to think about what happens. Because you don't want to think about those things. You want to think about the stuff that matters. Not, is this visible? Okay, what happens if I change it? Is there something that's going to break? If it is not visible to anyone else, it will not be able to break. You won't be able to break anything else if you update it. Packages. So what do packages do in Kotlin? So in Java you can have actually package level visibility. Kotlin doesn't have this, and many people argue Kotlin should have it. I don't know. There is one feature using annotations now available that actually, was designed for having experimental APIs, but it's now used much broader and has been renamed. That allows you to basically put an annotation, and the compiler tells you can only use this if you say, I'm using this version or this API, or I'm part of the API. If you have the annotation there, or you have used this annotation, and that kind of allows you to define your API into different slices. One of the things they use it to say, okay, this is experimental. These functions, you can use them, but you need to opt in because you need to be aware that they will change. They might very well change in the future because we don't yet know exactly what the right API is, but we make it available so people can experiment and give us feedback so we know better in the future what the right way of doing it is. So packages do a number of things, even in Kotlin. They provide a grouping for names, for class names, for function names, or for variable names, for field names, for constant names. And within the same package, names are always available with that name. You can, of course, have also the import statements that you can use things from other packages. But you have to import those. Within the same package, you do not. They also allow you to have multiple things with the same names in a different package happily coexist. Because at the JVM level, these package local names are translated in the full name, including the package name, but not in your source code. So if you rename a package, that's yet another API incompatibility. And API incompatibility as well. They also allow you to make programming life a little bit easier, to make sure that you can organize code that belongs together. So it's partially also to convey roles. So we have an internal package. That means that this package is not really intended for public use, so if you use it, be very, very careful. But there are some reasons, or sometimes there are related packages that you want to provide some visibility for. You can actually do that with the modern Java module system, but if you don't use that, which we wouldn't do in Android, then the only thing you have is the convention. But the convention has meaning. So that is why we would want packages. Okay, the factory pattern. So we had the factory pattern before. I talked about it. So this is basically the idea of a factory, is something that creates objects. If we have the transparent factories, we want to basically make it behave really, really like a constructor. But in other cases, we don't. So we want to get a type. And in particular, one of this pattern is that actually we make the implementation often even invisible. So in this case, result type implementation is not invisible, but it could be private. So we say, okay, you can't actually get at the implementation at all. Or the constructor becomes invisible from outside. So you get a result type, but you don't get which implementation. One particular use of that is when we use testing. So you might want to have the actual version hit a database, but in testing you might want to have a version of a storage that actually just either gives you always the same value, or it stores the stuff in memory, or it does something else different to basically be only there for testing purposes. If you have a factory, then it becomes very easy to just change the factory or put in a different factory for your test code rather than for your implementation code. There's different ways of doing that. And basically factory, or you can have a configuration. When we use XML, we have Java has factories built in, so you can have different implementations for the same thing. and it uses something called a service loader pattern to basically tell Java which implementations of Java XML parsing libraries are available, and then it has some logic there to load the preferred one. So then you can only load a package, and then it automatically have that package with that XML parsing library available for usage. Automatically, that's the one that's picked rather than the default one built into Java, which sometimes is a bit limited compared to the special ones. So that's what a factory is and where it comes in. So we just create an instance of the thing using the factory. And so in implementation, it's the same as the transparent factory that wraps a constructor, but in meaning it is different. Semantics. Then that was it. So are there any questions? I'd be happy to take any questions in the live chat. And otherwise, I will be available on Teams, also in the virtual P201. So virtual P201, there will be some people there. Some people have said that they will be available over Easter. I will be sporadically checking it. One thing that you may want to do is use the add sign for a particular person. I will also create a tag in this channel for the unit. So if you do add, I think it will be AP or I might create two tags, one AP and one application programming. And that will go to both Kevin and me, so we will be able to get a notification. So normally, if there's a message in the channel, you do not get a notification. But if you do an ad for particular people, then they will get a notification, even if they're not looking at that channel. So we will be having that. We will be looking at it now and then. Of course, there's also Piazza if you have specific questions. Any other question? No other questions? Okay, then of course we will have other questions there. Yeah, I've got one question. Did you find this works better than last week's solution? Well, I hope it works better than last week's. I hope. So yes, I did it with the first year students, and they said they liked it a lot better than Panopto, including better comments or questions. And hopefully this works better on your mobile phones if you do not have a computer. Okay, so yes, if it actually works better, I will keep it this way. It's not a problem for me to use YouTube instead. So it seems that everyone thinks it works better than Panopto, so we'll go with this. Yes, I will be recording the thing. I will post it on Brightspace. I will probably also be splitting it up and editing it a little bit. What will be happening next academic year? Hopefully by next academic year the mess will be sorted out. Although for many of you, you will be ongoing on placement and you would have to contact your placement company. But I expect that you will be able to do a placement even if the academic year starts a bit late. So you can start your placement any time between after the lectures have started, have finished in this year. Officially, you should kind of start after your after the exam board, after you've actually passed this year. I don't think they'll make a problem if you actually start earlier. But in this particular circumstance, that becomes a challenge. I mean, there might be some employers that are jumping for volunteers that come and do placements because many people are staying at home. Of course, you are fully entitled to also do that. Don't say anything else. But that is an option. So And yes, what will happen next academic year? We will have somehow getting you marks. The plan is to announce that this today. So there should be a department level announcement on the assessment. I've seen stuff happening, so we are just dotting the I's and crossing the T's for that, and then you will be knowing what exactly will happen for all your units. Having said that, we are very aware that this is exceptional circumstances and extraordinary, and we will handle it as if that. So please do not worry about this. We will try to make this go properly. So that is for next academic year. Yes, hopefully this whole thing will be sorted out by that time. That's October. That's many months to go. Okay, so anything else? Otherwise, I will stop the live stream. And any questions can go also. They can go also into the application programming team if they're not kind of one-to-one help sessions. Okay, so thank you for attending. It's always helpful to have people there that ask questions and give me some idea about, okay, this is not clear. And the nice thing about chat is that you are not actually interrupting my speaking, so you can much more ask questions. In the first year, people even answered other students' questions. Anyway, so we have now Easter break, so I'll see you after the Easter break. Of course, if there's technical or lab stuff, I'll be sort of around, and certainly this week we will be doing APE, but virtual 201. Make use of it. Last week we didn't have a lot of people use it. I'd like to ask you to use it, and and if you have AP and say Kevin is not on or I'm not on, we can come on more, but only if there's actual demand. And so tagging would be a good way of getting people aware. So if you need particular help for AP and there's no one on, try and tag us. You might need to wait a little bit longer because we might not be actually sitting there waiting for questions, but we will try to answer all the questions that are there during business hours. Because we still do things. So the exam, yes, the official notification of the exam will come, but there. So I shouldn't say anything about the exam at this point, but it should be announced today what is happening, and I don't really want to, go ahead of everyone else, but you will hear about that. Yes, have a good Easter break too, and take care of yourselves. Don't get too lonely. You might say, from what I understand, you're still allowed in most cases to go to your family, so to stay there if there's no particular reason why you couldn't. So don't be alone. I would say that is an important one. And take care, stay healthy. Don't think that just because we're remote, there should not be any context. Okay. See you. Good luck, and I will stop the live stream.